Hi, my name is Isaac Lara,
My name is Kieran Buckingham.
and this is our project to intensity distance relationship project.
Here's our Geiger counter radiation detector. It's a kit manufactured by RH Electronics. A link to purchase it, as well as this manual, will be found in the description below. For our project, we'll be using 4 different radioactive sources to measure the intensity of the radiation as a function of distance, to hopefully observe some 1 over r squared behavior in each of the graphs we'll make. Now, the 4 sources we'll be using are cobalt-60, cesium-137, cobalt-57, and Brazilian nuts, because why not? And they also have radium in them. So, keep in mind that all these sources are very safe to handle, meaning you can be around them for hours and hours and hours and never worry about getting cancer because they're low energy compared to things like uranium and plutonium. So you'll be fine if you use this for your own apparatus. Another thing to note is that they all emit beta and gamma radiation. And that kind of radiation can pass through the metal that makes up the Geiger tube in our Geiger counter. So they will be picked up in our window. But in the case of the Brazilian nuts, which emit alpha particles as well, the alpha particles, they're too heavy to pass through the metal, so those won't be detected, unfortunately. Alright, so here's a quick tour of our entire setup. Right here is the Arduino, which is connected to the computer and our Geiger counter circuit. And speaking of the circuit, here it is in all its glory. We'll go into more detail right here, and it was very annoying to solder. But yeah, and anyways, moving on to the conveyor belt here. The conveyor belt was very easy to make. It just has a motor and the belt and a little tip that holds the sources in place as they move backwards. Cool!
Okay, here's a breakdown of our code for our Arduino Geiger counter. At the top, we have 2 commands that help us communicate with the SD card. Our log period is 1 second, so every second we're checking the Geiger counter to see how many detections it's had. Our max period of 60 is for our counts per minute, and we're using pin 10 to interact with the SD card. Our counts and our CPM variables are what we'll be seeing in our serial monitor. The multiplier helps us do the math for that, and we have a variable to track the time. Counts plus plus is updated for every detection on every second, and we'll be using the serial monitor to detect output. Pin 2 is what interacts with the Geiger counter, and that writes to the SD card. We'll be using this label in front of our time on our CSV to track which source we're using, and the serial monitor will tell us if something fails with the SD card. This loop here updates the time variable, and then it does our CPM calculations for us as well. Furthermore, it outputs that CPM calculation to the serial monitor. And we're using the Lego EV3 with the Geiger counter. We're detecting time on the Arduino while running a constant speed over 60 seconds on the EV3 from our 5 centimeter distance to our 25 centimeter distance. Here you can see the Geiger counter interacting with our digital pin 2. This allows us to see output on the serial monitor at the same time as tracking it on the SD card. We are using the Arduino to power both the SD card and the Geiger counter with common ground, but this could easily be hooked up to 2 AA battery pack and taken elsewhere.
When the radiation enters the Geiger tube, it triggers a brief electrical discharge that produces high voltage pulses. These raw pulses are then filtered and shaped by a series of diodes, resistors, and capacitors, which are then sent to the 14-pin IC socket, which then converts it into a clean digital signal. The process pulses then activate the buzzer and LED components for immediate feedback. Additionally, they are also outputted to our Arduino board via its INT pin shown right here. And with this, we are able to log the radiation counts on our serial monitor. So before we discuss our findings, we need to bring up some of the shortcomings we faced along the way. And one of those shortcomings was that the LED and our speaker gave out during testing. But this isn't really that big of a deal because we could already tell that we were getting detections from our, I guess, command window on our Arduino program. So that really isn't that big a deal. And also we had to like meticulously check each of the resistances of the resistors using an ohm meter before soldering, as instructed by the RH kit that we were using. And it was really annoying just soldering on the board because we had to make sure that there was no crosstalk and that our beads were very good. So yeah, soldering is not fun is basically the gist of it. But coding, we didn't really find any issues with the Arduino code. The only issues we had were just path issues for the EV3, but that was resolved very quickly. We just had to use a different library instead of Pybricks. But yeah, other than that, this project went really smoothly. All right, with all the background established, let's now talk about the data we managed to acquire with our apparatus. Now, as a quick disclaimer, we also decided to measure the radiation intensity of our iPhones to test the old myth that iPhones are radioactive and can cause cancer. But anyways, let's talk about our data. In the y-axis, we have intensity measured in units of counts per minute, and in the x-axis, we have distance measured in units of centimeters. Now, for the graphs of cesium-137 and cobalt-60, we see a clear 1 over r squared relationship between the two variables. And this makes sense because in a gamma ray spectrum, the photo peaks of cesium and cobalt-60 are located at pretty high energies, at least compared to cobalt-57. For starters, cesium-137 features a photo peak at around 662 kiloelectron volts, and for cobalt-60, we see photo peaks at around 1100 and 1300 kiloelectron volts respectively. But in the case of cobalt-57, its most intense photo peak, as a matter of fact, is at around 122 kiloelectron volts, which is roughly 6 times less than the lowest of the two graphs I talked about previously. And this means that since it's lower energy, it's more likely to be attenuated in air, which means that air molecules are more likely to absorb this radiation rather than the Geiger tube. So that's why we don't see as much counts per minute in our y-axis for cobalt-57. And as a result, we don't see a 1 over r squared relationship between counts per minute and distance. But yeah, let's now talk about the Brazilian nuts. So you might be asking yourself, well, Brazilian nuts, they have pretty high photo peak energies. Why don't we see any sort of 1 over r squared relationship in this graph? Well, as it turns out, the main decay product of radium inside the Brazilian nuts is alpha decay, which means that it can't be detected by our Geiger tube because it can't pass through the metal that makes up the tube. So yeah, we can't register those counts, and as a result, we're screwed. And yeah, we shouldn't see a 1 over r squared relationship as a result. But in the case of the iPhone, the reason why we don't see a 1 over r squared relationship is because iPhones don't emit any ionizing radiation. In fact, the main sort of radiation they do emit is infrared energy, which isn't associated with radioactive isotopes, you know? But yeah, all the data that we managed to acquire with our apparatus, despite it being finicky, is very, very good. And I'm very surprised that we're able to get such clear graphs for cesium and cobalt-60. So yeah, I would say the results of this project were a complete success. So anyways, thank you so much for watching, and we hope you learned something, and hit like and follow and whatever, all that stuff. See ya.